Okay, dear students, let us discuss an important problem where I'll be finding the velocity of a transverse wave in a rope hanging from a ceiling, and I will discuss the various aspects of it, how the velocity of a transverse wave in a stretched string or a hanging rope is equal to square root of T by m, where T is the tension, small m is the mass per unit length. First, let us discuss how this expression gives you velocity. Let me do it dimensionally. Now, as you know, tension is a force, and let us see how T by m, square root of that, is equal to velocity. Now, suppose this is a rope and it is not horizontal, it is hanging vertically downward, say, from a ceiling here. So, length of the rope is L in the rope, and the total mass is m. So, in length L, total mass is m. So, per unit length, mass will be m by L. Mass per unit length of the rope, how much mass it has, is defined as total m over total length. I represent it as small m. Now then come back here, how square root of T by m is velocity. Now look, tension is a force, that is mass into acceleration. If you put it dimensionally, since it is a force, so dimensionally it will be mLt minus 2 mass, Lt minus 2 length, T to the power minus 2 acceleration. So this is force, and this I just explained is mass per unit length. So what happens, mm cancels, L comes to the numerator, so it becomes L square T minus 2 square root of that. That is same thing as L square by T square square root of that. That is equal to L by T. Length over time is nothing but velocity. So this part is clear to you, that velocity is equal to square root of tension over mass per unit length, not total mass, mass per unit length. Means unit length of the rope, what mass it has in it. Means if the length L has a mass m in it, L length has mass m in it, so unit length will have m by L. This is called mass per unit length. I write it as small m. So once this is clear, now let us go back to the problem. Now, as you can see in the diagram, here is a uniform rope. This is a uniform rope. Means all throughout the distribution of mass is uniform. Means if you consider 1 centimeter here and 1 centimeter here, the mass in 1 centimeter here and the mass in 1 centimeter here will be identical. Means if you consider any point here and any point somewhere else, the mass distribution is constant. That is called a uniform rope. Its total mass is equal to 0.1 kg, and the total length from here to here is 2.45 meter. It is hanging from a ceiling here. Now, if the free end of the string here is second horizontally like this, a transverse wave will move from this lower end towards the upper end. This is what I have shown you, how a transverse wave is generated. This is a rope. When the rope is second vertically up and down, the disturbance moves towards this side with a velocity v. Now, since the rope has a mass, so it has a weight. So at different points the tension will be different. Why the tension will be different, I will also explain. Now, this rope, the length is 2.45 meter. From this free end, I consider a point here which is at a distance from here to here is x. from here to here is x. Now, so a small m I have represented as mass per unit length. So this length, I'm interested to find the tension here. So below this point, x length of the string is hanging. Now unit length has a mass m. So this length x, so x length will have a mass m times x, mass, and its weight will be mass times g, mxg. To look it better, I write it as mgx. So to find the tension here, the length of the string that is hanging below this point is length x, and its weight is this. So and what is this m? Mass per unit length. Means I can write it as total m over total L gx. Now if I, and for this I have used a symbol small m, that is equal to mgx, right? So this length x, it has a weight vertically downward, that is mgx. Means at this point, due to the weight of this x length of the string, this is the tension. So your T is equal to mgx. And remember, small m is not the total mass, is mass per unit length. Now, since we just explained how velocity is equal to T over m, square root of that, so I put it, if I put the value of T, that is equal to mgx over m, square root of that, m cancels, so your velocity comes out to be square root of gx. Now in NEET examination they can ask up to this label. Now if you look at this expression, g is a constant, 9.8 meter per second square, and the value of x from this point increases to this side. Means for this point x is this much, for this point x is this much from here to here, for this point x is this much from here to here. So for all different points the value of x is different. Since this is different, the value of v is also different. Means you can say here v is proportional to square root of x, right? Means as x increases from this end to this end, the velocity also increases. Means the velocity of the transverse wave in the string is not constant. In NEET examination they might ask you, what is the ratio of the velocities, let's say at this point and at this point. Then suppose from here to here is 1 meter and from here to here is 2 meter. Then what, and the velocity here is v1 and the velocity here is equal to v2. Then what you have to write for v1, you have to write g times, if here from this point to this point is 1 meter, for x you write 1 square root of that is g into 1 is this. And if this point is at a distance 2 meter from here, then in this expression for x you put x is equal to 2. And if here the velocity is v2, then you write v2 is equal to g into 2 square root of that is equal to root 2 times this. Now you can take the ratio. Now v1 over v2, that is this over this, that is equal to 1 by root 2. So in a NEET label they can ask up to this situation, or they might also ask what is the ratio of the tension at two different points. Then you have to use this expression. And the tension will be different. Here x is equal to 0, so put x is equal to 0. Suppose they have asked what is the tension here, which is at a distance 1 meter from this free end, then use this expression, and for x put 1 meter. If they ask you what is the tension in the string at this point, which is at a distance 2 meter from here, then use this expression and put for x as a 2 meter. So the tension is also different. Means as you move up, the tension is proportional to T is proportional to x. Tension is proportional to x. Means if you consider 2 points, 1 point here, 1 point here, the tension here will be more, the tension here will be less. And the velocity is proportional to square root of x. So now we have find the expression for velocity. Now it has asked to find in the question, find the speed of the transverse wave in the rope at a point 0.5 meter distance from the lower end. From here, at a distance from here to here, let's say 0.5 meter. So what will be the velocity here? Then you have to use this expression. So your velocity will be g times 0.5 square root of that. Square root of that. Why I have drawn this diagram here? This was the diagram before the wave was generated. This is the diagram. This point is same thing as this point. This is the diagram when the wave is generated and it is moving towards the upper end, right? So if you put the value of g as equal to 9.8 and 0.5 and you take the square root of that, your velocity comes out to be 2.21 meter per second. What is interesting here, you must understand, this velocity is not constant. It depends on x, rather square root of x, means at different points the velocity is different. Now in the second part of the question, it has asked calculate the time taken by the transverse wave to travel the full length of the wave. Once the wave is generated here to travel to this end, what time it will take? Since the velocity is not constant, so you cannot write the expression speed into time is equal to distance. So T is equal to S over V, and S is given as, S means the length of the string is given as 2.45, S is given as 2.45 velocity, and this is a variable. So you cannot use this expression to find the time taken by the wave to travel from the free end of the rope to the end where it is hanging from the ceiling. Then what you have to do, you have to approach the differentiation method. Now you have to approach the differentiation method. Now we know for variable situations, we know if dx is a small displacement in time dt, then in unit time the displacement will be dx over dt. So that is your velocity, and in this case the velocity is variable, therefore you have to use this expression. If you cross multiply this, you get dt is equal to dx over v. Now where dx and velocity we just calculated as g x square root of that. Now when the wave was generated here and it was traveling to this side, at this point I had taken it. When the wave was generated here, I take t as 0, and the wave when reaches here, I take the time t is equal to t. I take the time as t equal to t. So So let us therefore integrate. So integrate this dt from t is equal to 0 to t is equal to t, means time taken by the transverse wave to travel from this lower end to the upper end. So that is equal to integration of this dx over, I rewrite it as g to the power 1 by 2 x to the power 1 by 2. Now to travel the whole length from lower end to the upper end. Now since g is constant, its square root is a constant, so it is taken out, so it remains like this. Now I am left with dx. I bring it to the numerator, so this looks like x to the power minus 1 by 2 from 0 to L. So this is g square root of this. So this can be rewritten as x to the power minus 1 by 2 dx from 0 to L. And you know, in integration, its power will be increased by 1 and it will be divided by the same number. So the integration becomes x to the power minus 1 by 2 plus 1 over minus 1 by 2 plus 1, and its value from 0 to L. Its value from 0 to L. So that on simplification gives this becomes x to the power 1 by 2, x to the power 1 by 2, and this becomes 1 by 2. This 2 comes to the numerator and is taken out. So I am left with 2 square root of g, and here x to the power 1 by 2, its value from 0 to L. Its value from 0 to L. Now, so that is equal to 2 over square root of g, where here I put the upper limit L to the power 1 by 2 minus, here I put 0 to the power 1 by 2, that is 0. So this is the time taken. I started from here, the left hand side. Integration of dt from 0 to t will be t. So this is equal to your t. This is equal to your t. That is equal to 2 times square root of L over square root of g. So I can write it as 2 times L over g square root of that. And the length of the string is given. That is equal to 2.45 meter. So I put it here as 2.45 divided g is equal to 9.8 square root of that, and it comes out to be 1.0 second. 1.0 second. So I hope it is clear to you. Now this part you can expect the second part of the question in JEE Main and Advanced, and at the most, if you are an aspirant for NEET examination, they might ask you what is the ratio of the tension here and here, what is the ratio of the velocity here and here. But the time taken by the transverse wave to travel from this end to this end is expected in JEE Main or Advanced, but not in NEET. And what you have to be careful is about these two expressions. Velocity is proportional to square root of x and tension is proportional to just x. Means as you move up, tension varies like this. As you move off, the velocity varies like this. I hope it's clear to you now. And since the velocity is not constant, so I had to use a different approach. In time dt, the displacement is dx. In time, the displacement is dx over dt, that is velocity. So if I cross multiply, I get dt as dx over v I calculated. So if I integrate on both sides, from 0 to t is the total time taken by the transverse wave to travel from the lower end to the upper end. Right side is integrated, and it finally and finally we arrive at this expression, right? 2 times L over G is the time required by the transverse wave to reach from the lower end to the upper end. And if they might change the question, in what time the disturbance from the lower end reaches half the length of the rope. Then in the limit here you have to vary the limit from 0 to L by 2. So I hope it is clear. Thank you very much.